Okay, so let's go ahead and get started. Like I said, this should only be about 20 minutes or so, maybe a little bit more than that, but it won't be long. But before I forget, remember last class I said that that activity you could, pass in after the midterm, before you leave today. So I just want to, let you know which tables I don't have. I don't have table 1. I do have table 3. I do have table 4. I don't have table 5. I have table 6, table 7, and I don't have table 8. Yeah, so table 1, 5, and 8. Just make sure before you leave today that you hand in the activity from last time so you get credit for it.
It's just, how you guys.
Right, yeah, the activity was the 6 timey diagrams and also the NOR latch. So that was the thing that I had on the, I had the NAND latch on the board. I wanted you to do the NOR latch. Okay. Okay, so the new topic today is a short one. It's a register. And then after you know what a register is, okay, this is important, guys. After you know what a register is, with also knowing the D flip-flop from last time, you'll be able to work on lab 5. Okay, now lab 5 is not due till the end of next week. It's due a week from tomorrow. Lab 4 is due tomorrow. How many people have finished lab 4? There's quite a few people. Okay, yeah, that's not too bad. Yeah, so if you haven't finished lab 4 after the activity, after you pass it in, that should be your next priority. Okay. So up on the board, this is just a repeat of what I had on the board at the end of last time, where I gave you the system Verilog code for a D flip-flop. And you're going to see that once you have this code, to model a register in System Verilog is just a slight extension of this. Okay. Now, another thing I want to mention, and I talked about this last time, but I just want to emphasize that this circuitry here, this is what you're adding to lab 4. Okay, I talked about this last time where, just imagine lab 4's diagram is over here. And then I want to have to write that all up. But like I said last time, okay, lab 5 doesn't have the decoder, so you're not going to be using the decoder for lab 5 that you have for lab 4. Also, okay, the mux where the output goes to AN. And you had on one input, you had like 4 tick mark, all ones. And the other one, you had 4 tick mark B1110. You're not using that mux. And then also, you're not using the neg output. Okay, so using everything from lab 4 except these things here. And then you're going to create this and connect it up to your lab 4. So essentially lab 5 is lab 4 with memory. Okay, you're adding additional memory. And even though each one of these modules is labeled a register, hey guys, it's a little distracting. I mean, I like it when people are discussing things going on in class, don't get me wrong, but it's just a little distracting. So, I mean, if you want to talk, keep it down a little bit. Thank you. So anyway, getting back to these 3 modules, even though they're all labeled register, this one's really just a D flip-flop, and this one's really just a D flip-flop because both of these are just storing a single bit. Okay, this module here is storing the validity bit. See, its D input will go over to where your validity checker is, and it connects to the valid output. Okay, so that valid output's either a 0, 1, and this D flip-flop is gonna be storing. Okay, and then this D flip-flop, that's gonna connect to the AND gates of your lab 4. Okay, because that's where your sign bit is of your results, right? It's either a 0, 1, meaning your results either positive or negative. Okay, so that's what these two flip-flops are gonna be doing. They're storing the validity bit, they're storing, or this one's storing the sign bit. Now this module, this is really a register, okay? Because registers store multiple bits. And you need a flip-flop per bit you're storing. So this register here is a 4-bit register. So it contains 4 D flip-flops. Okay, those flip-flops are connected as you see here. All the clock inputs are connected together. The D inputs come all together and make a 4-bit D input, and the Q outputs all come together and make a 4-bit Q output. Now, I didn't actually show it on here, but the sets and the resets and also your enter or enable, they're all connected together too. So for example, you know, like your sets, like each flip-flop would have a set and they would all connect together. And then you have a set input to the register, right? This is like your set input to the register, your clock to the register, your D input to the register, your Q out to the register. Okay, so registers are just a collection of flip-flops. It's very analogous to, I've called facilities about that. There's something, some crusher or some pipe or something that's rattling. So hopefully they get over here before we have a burst pipe or something. Yeah, so anyway, registers are just a collection of flip-flops, which is similar to the ripple carry adder, right? The RCA, remember that's a collection of adders, right? You would need an adder per bit. Well, here you need a flip-flop per bit. Did you have a question?
Yeah. Oh, why do we need to connect the T6 and T7, like the validity and the negative, to a register instead of just feeding it directly into the universal segment?
Well, just because we want to store that data until something happens and then send it to the module. So we're storing like everything that's going to be displayed.
Okay, but
like up here, see up here, this 4-bit register, see this is going to, you know, the mux that has the binary number.
Yeah.
Right. So this is storing the number that you want to display. This is storing the sign bit that you want to display. And then this is determining whether you're going to have a display. And this is controlling what's being displayed.
I guess I was just wondering why we needed registers at all, like why we needed to store it.
Oh.
Is it because it would be like asynchronous otherwise, and we want to keep it synchronous?
No, you don't necessarily have to store something. I mean, we're doing it as an example of storage.
Oh, okay.
Because there's cases where you would like to show, you know, some previous result until something happens, which namely here is going to be push a button.
All right, that makes sense.
Yeah, so yeah, you're right. There's some cases like, you know, when you want like fast updates, let's say, you know, like real time, like you're probably thinking like real time streaming or something like that, you know, where you don't have like a storage, but you know, this is more like what is the Evo, whatever it is, you know, you store some program and watch it later until you press a button.
All right, so
Yes.
for example, let's just say I'm trying to like for the negative part, we're storing that. But if we just hook that directly up to the segment decoder, so the universal 77, that's like the decoder for this.
Right. I'm going to talk about this coming up.
All right, but let's say if we didn't have it on the flip-flop or the D flip-flop that has the clock cycle, that means that even if I decided to change the numbers before updating the clock cycle, and we had it, and it was before negative, and now it's positive, it would still show the old number, just it would like update only or.
Well, essentially that's what we want to happen with the memory. We want the whole result to stay until we push a button.
Okay, that makes sense.
Yeah. Okay. Yeah, and you see, as you might notice here, this universal module here, Dr. Mealy's, it also operates off the clock because it's doing something called time multiplexing that I'll talk briefly about coming up.
Right, thank you.
Okay. All right, but getting back to the register, so it's multiple flip-flops, right? You need a flip-flop per bit. And in System Verilog, it's actually fairly easy to model a register once you have your flip-flop model, okay? Because all we'll have to do to model a register in System Verilog is take the same code for your flip-flop and then just make a few modifications. See, these are the modifications here. You'll just have to declare your D input for your register as a 4-bit input and declare your Q output as a 4-bit output. And then instead of just having Q assigned to just single bits, you have to assign it to 4 bits. All right. So like when you reset, you would assign Q to 4 zeros. Now you probably will have to put the 4 tick mark B. I don't think you can just put 4 zeros like that. Again, you get the idea that you just need 4 bits here now instead of a single bit, since the register is made out of 4 flip-flops. Okay. Now, you're probably not going to like when I tell you that, but see, you could have done the same thing for the RCA, like your ripple carry adder, instead of having a structural model like we had you do, and you could do a structural model for this. You know, just have a single D flip-flop file and then have a structural that connects it all up like you see here. But you could do the RCA where you just take a single full adder file and then do the same sort of thing. Just take your full adder and make it multiple bit input and output, and Provider will do the work for you. Provider will make this structural model for you. I mean, the reason we didn't do that is, we want to give you some experience with doing a structural model. Ripple carry adder is kind of a nice one to do, kind of thing. Okay, so the bottom line is for Lab 5, once you have this, and you send it, it's good. To get your register module, again, it's just a few edits to what you already have. So what I would do if I were you, when you're doing your Lab 5, is after you have your D flip-flop all simmed and it's working the way you want, just do a copy paste into another file that you have called register, and then just make these modifications. And it should sim good, as long as you made the modifications correctly. Did you have a question? Or?
Why don't we have to do like for defining Q like B comma or instead of
This here?
no the line below like
Oh, why do you have to put 4?
no why don't we have to put the B like
Oh, that's what I'm saying. I think you do. I wrote this down pretty quick this morning. So yeah, looking at it now, yeah, you probably would have to do 4 tick mark B. So yeah. Yeah, I'm not always so careful. And again, I mentioned this last time. I didn't try to make any errors with syntax, but if you use this directly, which I would if I were you, I mean, there still might be a syntax error somewhere, but you got most of it, if not almost all of it, right? Okay, so the next thing is your high-level black box diagram for Lab 5. So remember, the high-level black box diagram, that shows you your main inputs and your main outputs, right? So your overall design. So just like Lab 4, you're going to have your 2 4-bit inputs, right? The numbers that we're either adding or subtracting. You got your sub input. Now, one thing that's different in Lab 5 compared to Lab 4, and you might notice it over here, is that Dr. Mealy's module, it has an AN output with 4 bits, just like we had for Lab 4, but it has a seg output that's got 8 bits instead of 7. And that's because Dr. Mealy's module uses the decimal point that's on the 7-segment display. So, the 7 segments are 7 of the bits, and then that additional 8th bit is for the decimal point. Okay. But we got 2 other inputs. Okay, the 2 other inputs you're going to have for Lab 5 are the enter and the clear. Okay, so as we were just talking about a moment ago, that's the big addition of Lab 5 to what you had in Lab 4, is you're adding this memory. So if your overall circuit is working at the end, and let's say you start out with 2 plus 3 being displayed, right? You got a 5 showing up on your 7-segment display because you had 2 plus 3. Well, now, since we have memory, when you go to change the switches for the next test case, as you're changing those switches, your result of 5 should still be displayed. It should stay, the old result should stay displayed until you hit the enter. Okay, when you hit the enter, that's when the display gets updated with the new addition or subtraction that you're doing. Okay, so that's how you know if your memories work. Is, you know, when you're testing it on the board, you know, as you change your switches between test cases, if the display is changing, that means your memory is not working, right? Because the display should only change with when you hit the enter, because when you hit the enter, that's when the cues get updated with the new input data. Does that make sense? Okay. The other feature, the other added feature is the clear. Okay, and oh, I forget to mention that enter and clear have to be buttons instead of switches. Okay, your A and B are still going to be switches, your sub's going to be a switch, but we require that the enter and the clear be buttons instead of switches. On your basis board, you got 5 buttons. So just choose one button for the enter and choose one button for the clear. So what do you suppose should happen when you hit the clear button? Press the clear button, what should happen? Yeah, your display should show 0, right? No matter what was displayed prior, when you hit the clear button, it should go to a 0. Okay. And again, these have to be button inputs. Okay? If you don't use the buttons, I'm going to instruct the graders to take off like a point. I mean, they won't take off 3.5 points as long as the rest of it is working. But if you have it all working the way it's supposed to, but you're using switches instead of buttons for the enter and clear, I'm going to tell them to take off a point. Okay, I just want to, if for nothing else, I just want you to be aware that in the constraints is a whole nother little section for buttons. Okay. My computer went to. If you change your password because you got the old password in your head and you got to think about the new one until you get that muscle memory going. Did you have a question?
Yeah. So when we do the clock cycle for the clock, like is that automatically controlled by FPGA?
Yeah, I'm going to talk about the clock. It's a good question because remember, that's one of the key differences between sequential and combinational. It's sequential because you have memory, you have a clock. So what you're going to see is that there's an additional thing you have to do in the sim file since we need a clock signal. And then also in constraints, there's something very easy that you have to do. You have a clock, but yeah, I'll get to that. Okay. All right. So any questions up to this point? Because the rest of what I want to talk about is just kind of the suggested order to do things. You know, first create the flip-flop design source and then sim it, make sure that works. Then do the register. Like I said, if you got a working flip-flop to model the register, it's basically the same code. You're just making those modifications. Sim that, make sure that register's doing what you want it to. And then we provide Dr. Mealy's module here. Okay, this module, this universal seg module, it's doing what's called time multiplexing. Those displays that are on your basis board, they're all hardwired the same way. So if you were to just you know, hook up data to those displays without time multiplexing, the displays just show the same data. Like for example, in your lab 4, you know, you were just lighting up one display. You know, maybe the result was a 4, let's say, from your addition or subtraction. Well, if you were to light up all the displays with that same data, you know, going into your decoder, well, just all 4 7-segment displays would just show 4. You'd see 4, 4, 4, 4. Okay. In order to show different digits on those 4 7-segment displays, you have to do it with what's called time multiplexing, where first they put a number on the furthest to the right display, then they put a number at the next one, then they put a number at the next one, they put a number at the next one, and then it just keeps repeating. And it does it at such a rate that our eyes can't detect. We just see a steady, 4 digits, even though they're really not there steady. They're just flying by really fast and our eyes can't detect it. Okay. And time multiplexing, to model a time multiplexer, it's not trivial. In fact, you'll be able to look at the code because I don't have the file, but I have a text file of the code. So what you'll have to do for this is you'll have to do a copy paste, just copy the text and then create a file in Vivado and just paste it in. And that file is in Verilog. It's not in System Verilog. Okay. Dr. Mealy wrote this in Verilog. So when you go to, choose the file to put that code in, you got to make sure it's Verilog and it should end with a .v instead of a .vs. Or SD, I'm sorry. System SD. Yeah, okay. The other thing to watch out for, and I mentioned this last time, is when you do the paste, make sure you don't have lines that wrap around. Okay, because there are some comment lines in Dr. Mealy's code that are fairly long. And sometimes what has happened in the past is that half of that comment line ends up on another line without the 2 slashes. So now Vivado, it thinks it's code instead of a comment and, causes errors. Okay, so just watch out for that. Another thing about Dr. Mealy's module is that when he assigned the AN, or excuse me, he has it as display _enable. So it's DISP_EN, and he's got this as SS segs. Well, when he defined those, instead of defining it, 3 to 0 and 8 to 0 or 7 to 0, he did it the other way. He did, 0 to 7 and 0 to 3. So he made the most significant bit like the 0th bit, which again is not conventional. I think he's the only person that does that, that I know of. Well, anyway, the end result is, and oh, I forgot to put these on the table. So let me do that. For that table. This handout shows how to do the constraints with Dr. Mealy's module. So that's the so I only have one per table, so you can take it. So if you look at this, it's the opposite order like we did for lab 4. Right, because in lab 4, like for AN, you went top to bottom, 0 to 3, right? You went 0, 1, 2, 3. See, it's the other way, it's ascending instead of descending. And same thing with the seg. It just goes the opposite direction. Also, like I said before, we're using the split decimal point. So that's why you see 0 starting where you see it. For lab 4, we didn't have that connected. So, we didn't have anything assigned to that segment. That display or it doesn't. Okay. And then as was mentioned earlier, there's the clock. And if you look in the constraints file, at the very top of the constraints file, there's like 3 lines that have CLK. You just uncomment those 3 lines, and that will connect your clock to the clock on the board. Okay. Everything else in the constraints would be the same way. The switches, and then you'll see that when you look at the constraints, you'll see there's a section for the buttons. And assigning the buttons is just like assigning the switches. You just got to put in the name, whatever you call, enter and clear for the button that you're going to use. Like I said, there's 5 buttons. It doesn't really matter to me which of the 5 you use. Well, you'll have to use 2 of the 5, and which one to use is up to you. Okay. Okay. All right. So, you get this all SIM, you got your Mealy module all created. Okay, now it's time to make the connections, right? So you're going to make all these connections and then also connect it up to the various points in your lab 4. Now, here's where that activity that some of you have done, I think only a couple. And what's required, well, prior to today, I said that you have to do it by the end of today's class, but I've changed that, and I'll explain what the change is. But this next thing has to do with that, has to do with taking intermediate signals from your overall design and putting it onto the timing diagram. And it has to do with Mealy's module. When you look at these two outputs on your timing diagram for your simulation, okay, the segs and also this display enable, which is the same as AN, they're not going to make any sense. Okay, the simulator can't really deal with these time multiplexed outputs. Like the simulator can't really show you what's going on. Well, there's a number of reasons why, but anyway, it can't handle it. So when you go to sim your overall design, what you have to look at is you have to look at what's going into Mealy's module. Okay, because we know this works. So if you have the right data going into Mealy's module, then Mealy's module is going to be outputting the right data. So in order to look at these three inputs into the Mealy module, that's where you have to do that drag, okay, that Dr. Benson shows in her troubleshooting video, and you got to restart and then run the sim again. Okay, so that's why I changed where if you're not able to show me, you know, that technique that Dr. Benson does in her video for lab 4, you can show me next week for lab 5. Okay, because you got to do it anyway. Okay. So, you know, this is that's getting fun. Almost sounds like they're drilling. Doesn't that sound like a drill? Pipes or something. Oh. Once I'm done here, I'll call facilities. Okay, what was I gonna say? What was I talking about? We were talking about yeah, just, you know, these three inputs into Mealy's module. Again, this is the number, right? This is the value that's going to be displayed. This is the sign, right? Either, well, you'll see that Mealy's module, when it's a negative number, it will light up the dash of the furthest to the left seven segment display. Right? When it's positive, it won't show that dash. And then here's the validity bit, and when it's not valid, Mealy's module will show dashes for all 4 7-segment displays. Okay. Actually, when you go to copy and paste the code for this, look at the very top of it, the title page, because there's information about, you know, how this works. It will, you know, will tell you what the validity bit has to be, you know, for this to be displayed, and you know what the sign bit has to be, and all that kind of stuff. Okay. All right. Already talked about constraints and the buttons. Now, like I said, this is due Friday of next week. Let's see. Oh, this is important. Okay, prior to today, because we didn't have memory, right? Everything before today was combinational, no memory, no clock. Well, now we have a sequential circuit, right? We have memory. Anytime you have a sequential circuit and you have a clock, in your sim file, you have to put some additional code that creates the clock for the timing diagram. So this is the code that you can use to generate the clock in your sim file. And you put this code between the line that has UUT, right, the unit under test, and where your test cases begin, right? So you have your line UUT, your test cases are here. This code goes right in between. And you see what this code is doing. It's an always block. And as the name implies, always is the code is always running. Okay. So what this code is doing is it's starting the clock signal as a 1, and it keeps it a 1 for 5 nanoseconds. Okay, this number sign 5, the number after the number sign is in nanoseconds. You probably noticed that when you do test cases, it's number sign 10, right? Test case, and number sign 10, test case. Well, that number sign 10, it's separating your test cases by 10 nanoseconds. Okay, so this code keeps your clock signal at a 1 for 5 nanoseconds, then the clock signal goes to a 0 for 5 nanoseconds, and then it just starts repeating. Right, it goes back to 1 for 5 nanoseconds, 0 for 5 nanoseconds, and it just keeps repeating. So that's how it generates a periodic square wave, right? That's what we call a clock. So if this clock is a 1 for 5 nanoseconds and it's a 0 for 5 nanoseconds, what's the period of that clock? 10 nanoseconds, right? Right, period is just the amount of time it takes a waveform to repeat. You probably learned that in physics somewhere, or maybe even high school, right? Yeah. We use capital T for period. And then how do you get frequency from period? Right, it's the reciprocal, right? So what's the reciprocal of 10 nano? Well, what is a nano? 10 to the what? Very good. I gotta admit, your class is very good at that. I've had previous classes where they would say like 10 to the -6 for like micro, but so far all my sections have gotten that. So that's good. Yeah, it's 10 to the -9. And if you work that out, it comes out to 100 megahertz. And 100 megahertz, that's the frequency that the basis 3 board is operating at. Okay, so in your test cases, when you're using that number sign 10, you're separating your test cases by a clock cycle, okay, a period. Okay, I think the very last thing is right here on our diagram, it says bus mismatch. What do you think that means? What do you think bus mismatch means? What's a bus? We talked about what a bus is in the digital world. What's that? The multiple bits. Yeah, multiple bits. So if you have a bus mismatch, what do you think that means? Say that again.
Is that like where the most significant bit is how it's
not quite. I suppose that could happen, maybe. But look at the diagram. Look at this connection right here. What's mismatched? The bits. See, this is a 4-bit Q output. This is a 14-bit input. So that's a mismatch. So most of the time, if you have a mismatch like this, I think Bovado will still run. It will give you a warning, but it's possible that you'll still get the desired result. But how could we fix this? There's something that you learned a few weeks ago. It was during an activity where you can very good. Yeah, that you can join together bits, right? Concatenation. So you could do something like, you got T8 here, and the concatenate is the braces, okay? And you could put, well, what would you put here to match up? Yeah, you put zeros, right? Why wouldn't you put a 1 or something here? Why all zeros?
It's the same value. Like
yeah, because you want to keep this number the same, right? Remember, this is a binary number, right? A 4-bit binary number. So you don't want to add 1s to the left, nor do you want to add anything to the right, because that would change the value. So that's why you would just put whatever number of zeros you need in front of it. All right, so here you'd have to put what? 10 zeros, right? Because you're matching 4 bits to 14 bits. Okay. All right. So I think with all that, I think you have enough to do lab 5. Okay. So like I said, make sure if your table hasn't turned in an activity from last time, make sure you do that. And then after that, it's up to you whether you want to stay here and work on stuff or whether you're good for the day. I know when I used to take midterms, I was pretty beat after a midterm. I'd want to go sleep for a while. So you may want to go sleep, but Anyway, it's up to you what you want to do the rest of, the time here. Okay? Okay.
For the